Okay, I'm back. So we're going to talk about the continuous representation model, which we call CRM. And it's like it uses the same machinery that we discussed, the SPH machinery, but this time it solves like a different set of equations that helps us simulate the terrain. Um, okay, I'm going to skip this. Okay, so our end goal is going to be this. So this time, instead of um, fluid in a pool, we have this patch of granular terrain, and we will just accelerate the vehicle again for a certain amount of time and then brake. And you can see over here, notice some artifacts like the particles floating. We'll talk about that, like why that is. Um, but you can see the vehicle moving forward. Um, it's about, with the visualization, it's like about 10 times slower than real time. Okay, so this is what we'll be simulating. Okay. Okay, so what is the continuous representation model and how do we use it to simulate granular dynamics? So the basic idea is this. So what Luning spoke about in the morning, you is the most physically accurate modeling of terrain that you can do. You know that terrain is made up of particles. You assign, you say that each particle is like a rigid body. It could be different shapes. You can do that with like various clumps, like clump-like particles. But basically, you solve for the rigid body dynamics of each and every particle in your terrain. So this is like you break up the terrain into the discrete pieces that it is, and you solve you solve for the dynamics of all these discrete pieces. But obviously, like in a single cube of soil, you have like millions and millions of particles. So it sometimes becomes computationally expensive to do it this way. So in CRM, we take another approach. We view the terrain as a continuum. So it's some material, and we view the since we view the material as a continuum, we are only bothered with like the field information in this continuum, like what is the stress in this continuum, what is the pressure, and what kind of forces does it apply on like rigid bodies moving over it or like rovers moving over it. So the biggest difference is that going from like a discrete setup of the terrain, we now have one single homogeneous material that represents the terrain. And CRM is the machinery which allows you to model the terrain this way. So the difficult part, as you would expect, is like modeling this relation. Like given I move my terrain in this way, what are my stresses that are developed internally? Because that's what defines how much the terrain will resist deformation and how much it will push a wheel or something moving on the terrain. So soil is like a pretty funky material if you think of it like a material. So I motivate this with this hourglass. So here you can see some sand falling down. So the top of the sand, obviously I didn't come up with this example. It's a popular example. So the top of this glass, you have soil that behaves like a solid, like it's stationary. It's kind of like hard to shear. It's hard to compress. As you go down towards the restriction or the opening, soil starts flowing, right? So it's behaving more like a fluid, like it can shear, and then the shear rate is some property of like the internal friction. So it shears and goes down. Then once it falls out of this hole, is almost like a gas in the sense that the individual particles do not pull the other particles, right? So once you have uh, like the sand particles falling through the hole, there's no tension between the sand particles. They all fall like pretty much independently. So it behaves almost like a gas. So coming up with a constitutive model to model soil through these three phases is the real challenge. while applying it to SPH. Before I go into that all that math, from a high level perspective, in terms of Chrono, the CRM terrain fits into all the other terrains in this way. So if you consider simulation speed, some recent advancements over the past 1 year has made CRM terrain almost as fast or slightly slower than SCM terrain. Obviously, it is much slower than rigid terrain. SCM terrain, for those who are not familiar, is like the terrain model based on the soil contact model. So the soil contact model is good because it's fast, it's easy to implement, but then it has a lot of non-physical parameters that you need to do a lot of experimentation to tune. And this experimentation is not something simple that you would usually find in a lab, like an axial testing lab, but you need like a lot of apparatus, like you need a bevel test, and you need a lot of things before even you build the simulation model. Right. The CRM terrain, on the other hand, is more physics based because you define a constitutive model. So you kind of like can define material properties of that terrain. And if you find those material properties out, you can basically simulate your CRM terrain. So in terms of simulation speed, CRM terrain is still slower than SCM terrain, but it's much closer now than before. And then on the extreme right, you have the DEM terrain, which is like much slower than the CRM terrain and much slower than the rigid terrain because of the high degree of freedom count, because you're modeling each and every particle. Simulation fidelity. So this is the nice thing about CRM terrain. Although it's as fast as SCM terrain, you get more fidelity. Coming back to like the same thing that I said, you can define material properties. And I'll show you some examples where CRM terrain, like externally, CRM terrain has been validated to produce more realistic simulations when compared to SCM terrain. So you get some more simulation fidelity, but of course, it's not as good as a DEM simulation. So you lose out because of the assumption that the terrain is a homogeneous material, which it is not in reality. So this is how you put CRM terrain into like the other Chrono terrains. Okay. So this time much lesser math, I promise, and much lesser slides on that as well. Just some basics. Again, you have governing equations similar to what you saw with fluid dynamics. This time you don't have the Navier-Stokes, thankfully, but you still have them. You have a mass balance equation for the continuity, and you have a momentum balance equation, and you don't have an equation of state because I'll come to that in a bit. But these are two main governing equations that you have. You discretize these governing equations again using SPH. So it's exactly the same machinery that we described earlier. You'll go from the PDEs to the system of algebraic equations. You'll integrate them with some integrator. Again, all the options are available except the implicit integrator because we don't enforce incompressibility in CRM. So there's no point of having an implicit integrator. And for the constitutive model, the hardest part, we rely on this paper by Ken Cameron and a student Ranatunga from 2015, which basically defines like how would I relate stress and strain given that soil can behave like a solid, liquid, or gas. They use NPM in that paper. Just wanted to mention that, but we use SPH for the same like constitutive model. Okay, brief overview. You've seen these equations. This is the continuity equation. I made the D smaller, the capital D to small d, but it should actually be capital D. And then one thing you would notice here, instead of having like two terms like the pressure gradient and the velocity Laplacian, you just have one gradient of the stress. That's the major difference in the second equation, which begs the question: how do you find stress? Right. That's where the constitutive model comes in. You need to know what the stress is, and this is the method that we use for getting the stress. We assume that the model is linear and hyperelastic at first. This gives us equations that relate the stress rate to the strain rate. And we can, once we get the stress rate, that is d sigma by dt, we can integrate that to find the stress. We treat, so obviously sand is not completely elastic, right? It can flow, as I said. So that is plastic deformation and plastic flow. We treat, I think that's the next slide. Yeah, so we ignore that at first. Like we just take the total strain. This is like the total strain in the material, which includes like an elastic part and a plastic part. The plastic part is what I removed right now. So for now, we ignore it, but we come back to that a bit. So once you have this elastic part, you can use this linear hyperelastic elasticity assumption and get your stress rate, and you can integrate that to get your stress. Discretization, same as before. This is the slightly cool part. A lot of text on the screen, but um, what we do is we post-process the stress. So we assume complete deformation, right? So the strain can be plastic or elastic. That entire strain produces a stress. Um, that stress has that stress has to be limited by a yield stress. This is from continuum mechanics. But then since we did not remove the plastic part, the stress has gone way beyond the yield surface. So what we do in post-processing is we let it go beyond the yield surface, assume that there's no plastic part, and then map it back to the yield surface. And that means we take the stress, we kind of compute like how much the material has flowed, and based on that, modify the stress after our integration to say, okay, this is the new stress because you didn't assume plasticity and flow before. And that entire mechanism of doing that can be explained by like this this plot here. And this is the only thing that you need to know to set all the parameters for CRM. So what this plot defines is it tells you, given how much pressure I apply on the soil, like how much I press the soil, how much resistant is it to shear flow? Okay, so what this says is that ratio of how much resistant it is to shear flow is given by mu. So you can think of this like a friction coefficient, like in Coulomb friction model, right? The more normal force you have, the more resistance to friction you have, right? So this is like a friction coefficient. But then in granular terrain, what happens is once the material starts flowing, right? Once the material starts flowing, the x-axis over here is like an inertial number that kind of explains how much the material is flowing. So once the material starts flowing, the friction coefficient increases to a maximum, which is not like rigid body dynamics. Like in rigid body dynamics, you have a static friction, dynamic friction. Once static friction is done, you go to dynamic friction, and that's constant, right? But in terrain, like you can imagine that once you have shear, once you start flowing, the particles like lock more often. So there's more friction and more resistance to flowing. So for the same pressure, you would have more resistance to flowing, and you need a model to capture that, and that is this model. It's called the mu of I rheology. But this general intuition goes back and it helps define how the stress changes and all of that. So you don't need to know all of that, but this model you can define. So you can define what this initial mu s is, and that defines when is the onset of flow, right? For how much pressure, and if I have like this much pressure, how much force that I need to apply to initiate flow, that is defined by this mu s parameter. And then you can define this mu2 parameter, which is like the maximum friction that I can have, which is over here. And then the code will basically, based on what is happening, interpolate between this and use a mu, which will go into some equations, and you'll get like stress and strain. But as a user, you just need to know how to define these parameters. There are some more parameters like the curve this thing takes from mu s to mu2 uh, is defined for a few more parameters based on the particle's grain size, based on the particle grain density, uh, um, and based on the bulk density of the material. And these options are also available to set. But I'm not going to go into details of how to set those, because personally I use the defaults, and when you have like some new data, you can try to measure the particle grain size. Many times you know the particle grain size distribution, and you can use that information to set a particle grain size and a particle density. And you can also measure bulk density, and you can set that in. So that's the advantage of Chrono in the sense of CRM, in the sense that all of these parameters that you plug into the model to define this rheology are all measurable parameters. Um, which makes it more physics based in something like SCM. Yeah. So these are the parameters that I was talking about, like the density, Young's modulus, Poisson ratio, mu of I naught is like one of the parameters that goes into the rheology, and there are a lot of papers on how to set this parameter based on your material. It's a physics parameter, so it's not a magic number. Then there's the two mu's, the mu2 and the mu s. Usually we set mu2 and mu s to be the same in like all the, I mean, if you've seen those Viper simulations in Chrono, validated with like NASA data, it's when mu2 and mu s is same. So we don't really use the full breadth of the rheology model, but usually mu2 and mu s we set as the same and equal to the internal friction angle of the soil. And you can also set the average diameter of all the particles in the soil. And we also have this additional parameter called cohesion. This kind of like helps model that, like sometimes like the soil is not fully dry, right? And sometimes if you put wet soil in an hourglass, you'll see that the even when the particles are falling, they're not separate particles, they are like sticking together. This kind of like helps model that, although it's not like exactly modeling that, but if you want to like an accurate model for that is under in progress. But like if you want to like quickly like have something where the particles are not like fully disjoint but like kind of like are stuck together, then you can increase the cohesion and make the terrain more like rigid and less fluffy. But these parameters define your CRM terrain. All of these parameters except the cohesion coefficient, which I feel is a bit hacky. Other than that, everything is like physics based, and you can measure in the lab. Yep.
Density, I understand that. That a granular material or just particles?
No, so the first three are bulk quantities. So Young's modulus of the bulk material. Um, that parameter is actually a bit hard, I would agree. But I think it does not play a huge role in the dynamics of the system, is what I've observed. I actually don't know. uh, yeah, it's not easy to measure Young's modulus. We use 1e6. We use 1e6 as a default. I've tried going higher and I've not found much difference in the overall like output of the simulation. But of course, like I don't know.
All the time. So very difficult to measure these.
Okay, that's interesting. I mean, if there's a nice relation between these and the bulk density, it will help because you can eliminate then most of these parameters. um, but yeah, I don't know of any. I've not read any papers on how you can measure the bulk Young's modulus of something like sand. Yeah.
We can get into it offline, but it's pretty complicated. In, in regular, mechanics of materials, you have a material that's a solid, and like you said, different states. But this granular material, it can be all three states,
Exactly.
depending on the bulk density.
Yep.
That's the
Yep.
whole key.
Mhm.
The key is the bulk density.
Mhm.
So if you can tie everything back to bulk density, then you can start to uh, establish what your properties are. But without bulk density, you have material that can be anything depending on its state.
Yep. Yep. Um, I think the dynamics of the system would change with bulk density. Uh, But do the material properties change also with, but like, would I have? Pressure. Mhm.
That's the key to it. Right?
Yep.
You can define that state, you're back to the more cool,
More cooling friction.
and then you can start analyzing. But I don't completely understand what I is, but I do understand that the normal force is the basis of more cooling friction.
Yes.
So, the shear strength.
Yeah, this is.
Strength is our normal force.
Yeah. So this is, I think, what you're talking about, the Moore Coulomb, like the shear stress, the maximum shear stress that you can permit is this friction coefficient into the pressure that you have, and the cohesion parameter comes here, like, so you can like kind of like permit more shear stress if you have more cohesion, which makes sense, right? You're like, mm,
It's 3D problem. We're treating it just like a 2D problem, but it's not, it's a 3D problem.
I see.
So before, there has to be another loop on the whole analysis to determine what is the bulk density, and then you can run this analysis. But the bulk density changes with depth, so it depends on what depth you're operating in.
Yeah.
And then you probably correlate depth, bulk density, and then to the more Coulomb, and then run this as is.
Yeah.
It's just enough, I think it's just one more layer on top of this to informed about the bulk density. You know, I'm not an expert on this, so I'm just telling you from my point of view, what I see.
Yeah.
So that's just something I'm struggling to understand.
Mhm. Yeah, I think I agree. Like, I think that's what I, I've been struggling with this as well, because like if you do barometer tests, for example, like where you have a plate pushing against the CRM soil, you don't have the compaction thing that Robert is talking about, where the deeper you go, just because of the weight of the soil and the locking of the grains of the soil, the deeper you go, you have more resistance to shear. And that's really not modeled in this model. So if you take like a barometer and you keep pushing down, you'll keep going down. So that's like a intrinsic property of the model that we choose. And I've been looking at some other models that have this hardening concept where you can set a consolidation pressure. And as you increase that consolidation pressure, your yield surface, like where you yield, keeps going, becoming bigger and bigger. So like you'll yield much later if you have a higher consolidation pressure. Like one example is like the Cantley model. There's the Drucker-Prager model with like a cap for this pressure. But I agree, like there is like another player in. Oh yes, but yes. Oh, interesting. Yep, yep. No, I was sorry for the detour. But yeah, so this is one model. Of course, there are ways you can improve it by adding more fidelity to it and using like different constitutive models. It's something that I'm actively working on right now. Okay, new features. So this is all about the physics. I'm going to pause here for one more second if anyone has questions, and then I'll just go to some new features and results that we've got, and then go to the code. Okay. So we've done so the main goal of all these new features has been assumptions and speed ups. Obviously, CRM was not as fast as SCM before, but we felt that we have there are a lot of tricks, I like to call it, that could speed it up. And these are all SPH tricks more than more tricks on the constitutive modeling. So the one thing that we use, which is already commonly used in many other tools, was like we optimize like the neighbor search part. So if you remember in the SPH equations, like for finding the properties of anything at a point, you need to sum up the properties of all the neighbors and add them up. So we optimize this part. Um, we use a new data structure called like we store at each time step the neighbors and then reuse them across time steps. So that's what we do. So even though like if I'm particle I have at the start of the time step um, 10 neighbors, and I store the IDs of those neighbors. And as I go propagate in time, I only know about these 10 neighbors. They might have left my neighborhood or new particles might have come into my neighborhood, but I don't consider them. And the user has an option to set for how many time steps they want to use this neighbors list. So the more time steps you use it, the staler your information gets and the lesser your accuracy gets. But neighbor search is like a big computational part of your simulation. And so if you say I want to do neighbor search every 10 time steps, then your simulation is probably going to be 2 to 3x faster. But obviously it's going to be less accurate. We kind of tried to like understand how less accurate it is. And for that, we used some experimental data that we had for the MGRU3 rovers, some slip slope curves. So as you can see here, the gray line is the experimental slip slope curve that we got. Not we, like NASA Slope Lab conducted these tests. The orange line with boxes, the DEM results. So you do the same simulation with DME, which is what doing present in the morning, and you get the orange line with boxes. And then all the other lines are doing the same simulation with CRM, but we vary the frequency of neighbor search. And interestingly, we found that even when you go to like frequency of 10, the outcome, the slip slope curve, is basically the same as frequency of 1, but the simulation is like 3x faster. We also did this, we did this with like 4 other benchmarks. Like there's a paper, and this is the paper that we just submitted. But you can do this also with something like a razor. I should have really put a picture of the razor here. But the razor is a robot which digs soil by with rotating drums. Robert is actually the person who invented it. But we measured like the driving torque. So as it digs the soil in DEM, and that's the noisy orange dotted line that you see here. And we did the same measurement in CRM, but with different frequency neighbor search. So frequency 1 is like the default, right? Like you do neighbor search every frequency, you have no loss of information. Frequency 10, you do neighbor search every 10 time steps. And we found that this basically overlaps. We did this for also one more traditional test where you have a sphere that is just dropped into the soil, and you have like different spheres with different densities dropped into the soil, and you want to see how deep it goes, and you can compare. It's a very simple experiment that you can do in reality as well, and we found like similar results. One, that the CRM simulation closely matches the experimental simulation, and two, that changing the frequency doesn't really matter. Uh, the other optimization we did is we took inspiration from DME, so the active box concepts, and applied it to CRM. So this is how it looks. So if you have like a MGRE3 rover wheel, and you have this outside yellow box as like the computational domain, you can put like another box, which is the active box, around your rover, and the core and CRM will ignore all other particles. It'll store only these particles and do dynamics for these particles. It's a little bit more complicated than the DEM approach because you have a kernel in SPH. So at the edge of the active box, you still need to consider particles that are outside the active box. So it's a bit different in implementation, but the idea is the same. And of course, this speeds up simulations by a lot. The other thing that it helps with is is that like memory. So because I'll come to that actually in the next slide. But before, okay, so we've also found that active box don't lead to a lot of difference in simulation results. So this is now again those two plots from before that I showed you, where we apply an active box around the wheel and the razor drum. And we find that when you have no active box or active box, the results are pretty much the same. And to gain some intuition about this, it's because in soil, like the particles are not, like the continuum is not as continuum as like a fluid. So information travels much slower. So if you push something, it dies out. Like you push sand, it's not gonna like a wave, create a wave of sand. So you can get away with using these active boxes because um, um, you don't really, the dynamics of the particles outside these active boxes does not really affect the dynamics within, like does not really affect the dynamics of the wheel. So this is like the intuition behind it. So if you choose an active box that you're comfortable with, saying that anything outside this active box is not going to affect how my wheel moves. Um, okay. Yeah, so I'll come to that. It's like one of the future slides. So accuracy wise, you saw that it's good. Oh, it's this slide. Okay. So I missed a slide. Oh, I'll go to this slide first. So this is like using the active box. And one benefit of it is because you only store memory for the particles in the active box, you can do really large simulations. So this is actually a nice rendering of the simulation that is part of the tutorial. Um, and what we did is we scaled the terrain length. So there's a log scale from 20 meters, which is what you'll see in the tutorial, all the way to, I guess, on the H100, 1.5 to 2 kilometers. And you can see that it scales, it first it can do like such a large simulation. So there are no like memory bottlenecks anymore. And it scales decently well. So this line is the linear line. After like a certain occupancy is reached on the GPU, you can see that it scales linearly. So if I want like a 2x bigger problem, I'm going to pay a 2x price in my real-time factor. But before that cutoff, you can say that it scales pretty sublinearly. So you can get away with simulating, say, 1,000, like 1 kilometer of terrain in an RTF, which is closer to 20 meters of the terrain. So this is one other benefit of using active boxes. Okay, so coming to the RTF, we benchmark this across like 5 different simulations. So this is just like static baffles, rigid baffles, and you have like a terrain, like a granular material model with CRM with an initial velocity. So pushing the terrain goes and hits the baffles. Then you have the racer. This is the full racer vehicle, and you see these drums. They actually like rotate and dig the terrain. The yeah. Then you have like a tracked vehicle on CRM terrain. Over here, it's very light, but you'll see like a thin cable here, which is like modeled with FEA. So you have like a dam break with CRM terrain. I don't know what it's called, but like a dam that breaks and then it pushes the flexible cable and makes it bend. This is like one of the last states. And then you have the entire Viper rover simulated on the CRM terrain. So the baseline RTF that you see here, so the real-time factor is defined here. It's a wall clock time by the sim time. So a higher RTF is worse. So the baseline that you see here is the code from 1 year ago. And then this is the next 3 columns are the current code with the optimizations. So if you just use, if you use no assumptions, so no active boxes and you do neighbor search every time step, you still get some speed ups because of some other optimizations, but they are limited to like 2x, 3x. But if you do neighbor search less often, you can get another order, not an order of magnitude, but half an order of magnitude of speed up. Then when you use active boxes, you can get like an order of magnitude speed up. So for the track vehicle, you can see that it was 356.9 RTF, which means to simulate 1 second, you need 6 minutes. But now you can do that in like half a minute. And then we also compare this with SCM. So in SCM also there's like an active box, although it means something different. But with not using active box, you can see that this is 26.4, which is slower now than the CRM with active box and this other neighbor search thing. And with active box, you get closer to the CRM. But in this case and in this case, which is why I picked it, it's faster CRM. But of course, I'm not saying that SCM is slower than CRM in all cases. Yep.
Yes.
Okay, so they're the same, except this is all code optimizations that don't make any assumptions, like not doing neighbor search often. So we started using some more shared memory in our GPU kernels. We started like storing memory more efficiently. So this is like raw code optimizations, and then from baseline to PS1. Exactly, pure CUDA-based optimizations, and then actually one of the major players in this speed up is that before, there's actually more to say that why the baseline was slow rather than PS1 was fast. But before, even though we have an explicit co-simulation, like we exchange information, we used to step the MBA system, wait, and then step the FSI system. Now we just have another CPU thread that launches the FSI system and steps it. Sorry, the SPA system and steps it. So that's like almost like a guaranteed 2x, not guaranteed 2x, but like 1.5x right there. So that was actually one of the major improvements for PS1, I would say, more than like the micro optimizations. But yeah, then from PS1 to PS10 is assumptions in SPH, and PS10 to PS10 active is adding that active box, which is again assumption that nothing outside the active box matters. But if we for our applications, which are these, we found no difference in the accuracy. So you might as well use these assumptions than not use them. Okay. Um, so yeah, my last slide to sell you CRM, I promise. But it's one advantage of SCM over SCM is not many empirical parameters. Although you saw that there are some parameters that you still need to think about. The other thing is it's been pretty well validated at this point, because NASA has been independently trying to like find the difference between the different chronos. So they published this report very recently, like 2 months back, and you can see like slip sinkage versus slip curves. And what they claim is that Chrono CRM and DEM are the only ones when compared to like Chrono SCM and DARTS Becker, which is similar to SCM. The Chrono CRM and DEM are the only one that produce a sinkage slip curve that's physically viable. So of course, there's no experimental data here, but it just says that the sinkage and slip produced by these two are like make physical sense. Yeah. So and now with these optimizations, it's pretty fast now. There are people in the lab who are using it for reinforcement learning to train control policies and do like system calibration with some real data. And so it's pretty fast, and I think it's competitive now as an option for roboticists as well who preferred using SCM. Okay. So now for the coding parts, I'm going to talk a bit about the structure. Um, so it's the same code, right? It's the same code base. You're just solving one extra equation and you have this post-processing thing. So all the structure things that I talked about, like the class structure, remains the same, except if you want to use CRM terrain, you don't need to, but I would advise you to use this CRM terrain class, which makes things even easier. Um, you can directly use CRM. I'll show you an example of that where you can go from the old fluid simulation and replace the fluid with terrain with like a few line changes. We'll do that. But otherwise, if you want to use CRM, use this CRM terrain class because it fits in with the Chrono vehicle module very well. And you can interchange the CRM terrain for SCM with like a few lines of code. And it's very easy. So yeah, the CRM terrain class is useful. Okay, another example that I deal with is generating the CRM terrain patch is hard. There are many options though. You can just say it's a box like before and give it like the dimension of the box, but you can also now add this CRM terrain using a height map. So if you define like a height map um, as a image file or like I forgot what are all the options, but we'll look at that. But you can define a height map as an image file, and with that we can populate like the populate and make a CRM terrain. And also you could just draw like I want each and every SPH particle to be over here. So you can provide like SPH marker files. They're just like CSV files that define XYZ for each SPH particle and feed that in, and you can generate terrain that way as well. So we'll do an example where we go from the rectangular patch, which is what is the default right now in the tutorial, and like change it to do a height map. Okay, the other benefit is that you can now do deformable tires on deformable soil, because Chrono has an FEM module, and we have ways to communicate between flexible solid and CRM terrain. So you can do that, and we'll have another example where we just switch on a flag and go from rigid tires to deformable tires on a CM terrain. This demo is actually the one we used in like a paper that we recently submitted, and we found that it kind of makes sense when you go to deformable tire, a deformable terrain with deformable tire, your velocities, uh, like the velocity profile of the vehicle kind of makes sense. But more details about this are in the paper. You should probably read that. Okay, so I'm going to do a show and tell. It's very scary for me because I'm going to like live code, but we'll be changing the fluid simulation that we had in the previous tutorial. So if you remember, it was like a vehicle moving over a floating block, but now we are going to just put soil, and so the block won't be floating; it'll just be flat on the soil. Let me see if I have. Okay, so for this, clone the same old repositories. This time you can't use the zipped file from Dan because I did this after he sent it across to you guys. So if you want to see this demo, you need to clone the repository. You can clone Chrono if you want, because that is where I'll be copying the lines of code from, because I don't remember it. But the file name is easy to change from fluid.py, and that's the file that we'll be modifying. So I'm now gonna. Okay, so this is the easy to change from fluid file, and I copied. This is how I made this. Is like you can see I didn't forgot to change the comment, but this is from the old demo. I just copy pasted the code into this file, and I commented out the portion that sets the fluid properties and the SPH parameters, because this is the only thing that defines whether you're modeling fluid or soil, right? So I commented this out, and you can follow along with me or you can do it yourself, but I'm gonna generate appropriate soil properties and appropriate soil SPH parameters and run the same simulation, and we'll see what happens. And as you would expect, I'm going to copy paste. So I'm going to go to the terrain tutorial that I've made for this demo. That should have terrain properties. So I'm going to go scroll down. Oh, these are the terrain properties. This is how I need to set it. I'm going to copy paste it. So go to that tutorial vehicle CRM terrain wheel vehicle, which is like the actual tutorial for this, actual demo for this tutorial. And I'm going to try to paste this. So as you would see, like because I use cursor, it finds out that I'm doing something wrong, right? I in this demo, I don't have terrain. I don't have CRM terrain. And it's saying, look, use sys because that's your system. I'm just going to hit tab, and I'm going to hit tab again. Great, this is fixed. But what cursor does not know is that uh, these parameters are not like perfect for CRM. And also, I'm surprised it has not. Oh yeah, there it goes. So I haven't defined density or anything, right? So it's saying, okay, use this. Sure, I'm going to use that for now. Spacing, I don't know why it's asking me. Let's see if it has it, because I remember it was there. Spacing is there, so I don't know why it's asking me to change that. Sometimes you don't listen to it as well. But yeah, so I'm gonna use, okay, so I'll use the spacing that was already there. I'll use RK2, sure. I'll use D0 as 1.2. good enough. Kernel threshold, don't need to worry about it for now. Artificial viscosity is pretty high. Let's continue using it though. Shifting method, I'll use the PPST one. These are all actually defaults. The 3.1, 1.0, but I just have it there. I'm not going to use spatial constant discretization. I'll use the bilateral viscosity method, and I'm going to use the Adami method. Just checking if friction, Poisson's ratio, Young's modulus, density. Okay, great. So now I'm going to go to my computer. So this editor is SSH'd into computer. I'm going to try to run this file. So I'm going to the CRM folder. I'm just going to do a git status to see if the update has been, so you can see here, easy to change. So we're just going to see quickly if I hope that I've only changed those lines of code. It's problem with, yeah, so you see that I've added the density parameters for these things, and then I've set these parameters and everything else is the same, right? Yeah. Spacing not defined. So AI was right. Oh, it's called initial spacing. Perfect. So you see that now it's not floating, it's just a CRM terrain. You see the velocity field is pretty bad, so you would want to like increase the discretization a bit. Just running it again. Okay. So yeah, that was simple enough. On the next one, I'll give you some time to try it out yourself before I implement it. But any questions on this? Yeah. Yes.
Hardware themselves, they are defined as double, which is floating point 4, and a lot of GPUs that in comparatives are not really double person. It's not at the 64. Although you show H100, which is great for 64. But RTX 4080 is cannot really calculate double precision. So how did you parallelize? How does it work in some other GPUs?
Okay, so first the parameters are doubles, but the states are all floats. And we leave that to the user. So when you, in PyChrono, you can't, but if you build Chrono from source, when you build it, you can, and you enable the FSI module, you can choose whether to use double precision or single precision. And the code that I just ran, everything is single precision, except the parameters and the parameters that, okay, in this case, except the parameters that is, everything is single precision. So to answer your question, like, although you see that the parameters are doubles, everything that's running on the GPU is single precision for this example, but you can run it on double precision. Of course, it'll be much slower on consumer grade GPUs because there are not many double precision cores, right? So it'll be much slower. So to give you a number, I think it's like around 3x slower, moving from single precision to double precision. Yeah. Any other questions? Okay. Let me go to the next show and tell using height map. So for this, we'll be changing the rectangular patch. Actually, let me first run the existing demo, right? So this is what the existing demo is, right? It's like a rectangular patch. I hope I can zoom out. You can probably do it on your local computer because it's hard because but it's just a rectangular straight patch that the vehicle is moving over. We're going to try to change this. It'll still be rectangular, but we'll have like some kind of bumps. And that is what the next tutorial is going to be about. Okay. So for that, you will see the change to height map Python file. And if you scroll down, there'll be, or just search to do, there'll be a portion of the code that I commented out from that demo that you just ran. And this is the terrain construct function. So the terrain construct function is what defines whether you use a height map or rectangular patch or like SPH marker files. So this code that is commented out, you constructs the terrain as a rectangular box of terrain length, terrain width, and depth 0.25. It sets the position of it, and this is for again the BC markers. I want BC markers. I want BC markers on all sides except the top because uh, the top the particles can fly. Oh, also by the way, okay, but let's finish this and then I'll tell you one more thing. But now we'll try to do this with a height map, right? I'm going to wait for 1 minute, but what I would do is I would go to the Chrono source code, look at a demo, because for sure there should be a demo that does height map, right? So this is the demo, and see the C++ code, right? So you see create a patch from height map, terrain.construct, blah, 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 blah. I realize over here that, oh, you need a BMP file, like a image file that defines the height of the terrain, right? So I need a file, I need a length, width, I need some extra parameters. I don't know what they mean, although it's written here as like height range. I need depth. I don't know what uniform depth is, but I need all these parameters. I would then go to the source code and go to so this will take you to the CB file, go to the header file, because that's where the comments are always, right? So as you can see here, there are many construct functions that are overloaded and has a lot more information. So construct SPH particles and optional BC markers from height map. The image file is read with STB, and the number of channels defined in the input file and reading the image is 16-bit. So it gives you the information about what image files would work here. It tells you supported image formats, JPEG, PNG, BMP, GIF, PSD, PIC, so anything basically. So you just need an image file with like 16-bit value, so 0 to 256. And then you need, what this does is it creates the SPH particles at the patch specified in X and Y dimensions. So you can specify the patch. So you can have like a image file that's like 3 pixels, but you can scale that based on the patch that you want. You can set that with this function. The height of each grid point is obtained through bilinear interpolation from the gray values in the provided image height map. So think of the image file as this way. The image, each pixel at the image is 0 to 256. You specify a height range 0 to 0.3, and your 0 to 256 scales the height. So you can have 3 pixels with 100, 120, 256. The 256 will become 0.3, the 100 will become 0.1 height, and the 0 will be 0. So if I scale the height that I get of the CRM terrain is going to be the same as the pixel intensities in the image. Okay, so I guess that is enough information, right? Like one other thing is maybe uniform depth, which is confusing, and I noticed that it's not mentioned, but I know what that means. So it's basically actually I'm not going to tell you, like you should just try to switch that off and see what happens. It's like, okay, we'll try switching that off and seeing what happens. Okay, so I have enough information of how to change, right? Like from the rectangular patch to the height map. So what I'm going to do is I'm going to go back to my editor and try to do that. Great. So as you can see, AI is prompting me to do the same thing, but I'm not going to do that, right? I need like an image file. So I'm going to do vehicle.ch. Nah, that's not the right API as well. So I'm going to go back because I have bad memory. Get data file. So if you do actually, okay, that's right. Let's accept this and see what else it got wrong. So it got my height map. Great. The file that I wanted because I mentioned it here in the comment. This parameter does not look right. Oh, it's right. So it just takes doubles, terrain length, terrain width. Great. This height range in C++, this is like a CH vector, right? So it got that right. CH vector 2D, 0 to 2.25 to 0 to 0.3 to match that. I got the next parameter wrong because now it's uniform depth, right? And it's putting a number here. So this should be removed. Uniform depth, we'll set it to true. The other parameter is like the patch center. Thank you. So that's like the depth of the terrain. So let's do that. So that actually is a bit confusing as well. It's not that documentation, but height range and depth is a bit different because height range is on top of the depth. So you'll have 0.25 of depth, and then your height range is from the height map. And then true uniform depth true. Patch center terrain. Let's do this at terrain length by 2. And that's actually a better way of doing it. So forgot to type. Oh, okay. So it's not the same. As you can see, now we are choosing to have BC markers only at the bottom plane, and everything else is periodic. So you have a patch, and all the sides of the box except the bottom have periodic conditions. So particles can leave, come back that side, but it doesn't matter because it's like an infinite kind of terrain that you're trying to simulate. Okay, I think this should be it. Thank you. This would be much easier. Actually, this is how I like developing. I move this file into a Chrono repository and just paste it there because your IntelliSense will work better. And also, if you have a co-editor that is like an AI co-editor, it will look at the other demos and autocorrect all of these things. But now there's not enough context for it to autocorrect. So see, terrain is also spelled wrong. Okay. I hope this works. So let's try and I spelled construct wrong. Okay, great. So as you can see, this BMP file, which we'll open later, basically defines this kind of like height. I don't know if you can see it here, but it's like circular regions that like it's like a pie almost. It's like a bump actually. That's what it's called. So it's a bump where slowly the terrain is increasing in. Okay, so this is what I wanted to point out. You see these particles flying and staying there. That's actually the active domains artifact, right? So you have like this box that is attached to the vehicle. In the next run, I'll actually show you this box that I've used in this simulation. Don't fall. Okay, so I'm going to run this again. So all of this you can like play around with. So BC rigid, I'm going to switch on to show the rigid markers, and I'm going to switch on active domains. So you can see here the boxes are around the wheels, and you have this computational domain box, and you have BC markers at the bottom. Oh, I didn't- for some reason. Okay, but once the particle leaves the active domain of the wheel, it's going to be stuck because the code does not know, like does not care about it. So this is an artifact, and we are working to try and find ways to fix this. But any new way that we come up with is slower, like it makes the code slower. So we haven't released anything yet, but we are trying to fix these artifacts where we have these flying SPH particles sticking around. Okay, so one more thing I promised was change this to false. So let's see what that does. This is like the uniform depth. Hmm. So I don't know how I will show you this, but if you go all the way down and look from below, you'll see that the BC markers have moved up, and you have uniform 0.25 meters depth along the entire terrain patch. So below this bump, it's not like there is 0.25 meters and then the bump. It's uniformly 0.25 meters, and so the bottom surface like moves up. But I realized I can't show you that because I'm not able to like rotate for some reason on this computer. Oh yeah, actually, nice idea. Yeah. So for doing this, there's this flag called visualization SPH, which you can set in the visualizer. So yeah, and boundary markers needs to be set to true. Let's also set the rigid BC. Hmm. Hmm. Yeah, I actually don't see the difference. Oh, that's good. I don't know if you guys tried it locally, but I don't see any difference. So that's something we need to check. But ideally, what it should do is it should make this like a hole below. Um, Not a hole below, but like the surface elevated where the bump is, so that you have uniform depth. That doesn't seem to be working in this case. Um, yeah, something to check. Sorry about that. um, okay, so that was the height map. Any questions? Yes. 0.25, yeah, yeah.
But how did you solve correctly the interaction between wheel or tires and soil? Maybe that's not enough.
Yeah, for sure. So this demo, like the ones that I showed in the paper, they are much deeper. Um, like the depth is much higher because of that very reason, in the sense that it's you have like your space particles are sandwiched between two BC marker layers, and if you need to make sure that um, when when these two BC marker layers are pressing against each other, you have enough number of particles in between to resolve the equations correctly. Is that what you're concerned with?
Kind of.
Mhm.
Need to have a given steps of the solution for
For the
tire particles. That friction and forces that are
Okay.
acting on the
Yes.
site correctly.
Mhm. Yeah.
So I'm wondering if this is an issue for you or not.
Yes, for sure. Like so, the I think I think the actual results where we got some physically meaningful results used half the spacing that we're currently using and more depth. So we got a lot of particles in the flow in the surface as well as a lot of particles on the terrain on the tire uh, to resolve the friction. But I have noticed that this plays a crucial, like very important role in matching or in getting physically meaningful results. Like all the tests, this is one of the things that I run a lot of simulations on to get the right initial spacing and the kernel radius. So it's not just it's about stability and accuracy and also speed. So it's like a tricky thing to balance. But um, personally, I approach it more so from uh, getting it to constantly produce the same results over a range of delta x and h. So like some sort of convergence study. But it's hard to do in SPH. Okay. Nice. Okay. That'd be interesting. Yeah, because with variable resolution, like for example, in this case, if my tire had like very thin grousers or like some features that I want to capture, I need my markers to be the same spacing as my terrain. So if I to capture these grousers, if I go to a very fine resolution, my entire terrain has to be a fine resolution. My computational cost goes crazy. So yeah, I'll be very interested in doing the variable resolution stuff. Okay, so using the height map, the final show and tell is changing to a deformable tire. So for this, go back to like the main tutorial file, which is tutorial vehicle CRM terrain wheeled vehicle. Go there. This is the file. And in this, if you go to, so I've already set things up over here. If you were to manually add code without the if conditions that I've set up, you would need to do like two things. One thing you would need to do is add a JSON file that describes the parameters of the deformable tire. Find this. Let me go to the source code to show you what this means. What am I doing? So all your data files are usually stored in source, not source, data. It's like ton of data. Vehicle is what we're interested in. Polaris, because that's the vehicle. And yeah, this is the JSON file. There's probably an easy way to find it, but so yeah, so you can see that we set this vehicle, we define this tire, we define how many nodes that each element has. We define its material properties and some other like parameters for like the FEA stuff, which I'm not an expert on. Like over here, you have like layers of FEA elements that define this tire. But you just need to supply this JSON file, right? So from rigid, I'm going to ANCF. There's a bit of a Python hack where I say, if in my file name you find ANCF4 tire, then I'm using FEA tires. In C++, this is much cleaner because in C++ you can actually access the class. So let me show you how this happens in C++. So in C++, I can, if I'm able to cast my tire to a deformable tire, so you can use this dynamic cast hack to kind of see if you have an FEA tire or not. Unfortunately, you can't do that in Python, so this is like a hack so then once FEA tires is on, let's see what else you need to change. You need to use a different solver. We found that the Intel Paradiso solver is good, and we manually set the number of threads for each component of Chrono because now you're solving this linear system and you want more threads for that linear system, so parallel to solve it quicker. So we set that to 8, along with like this number threads Chrono is just like the number of threads for all the different matrix multiplies. So that we need that also to be high. We don't have a lot of collisions, so one is good over that. So we need to set that and just go. Okay, great. So that's one thing we need to set. But as you know by now, since you're using an FEA tire, you need the FSI system to know that it's an FEA tire now, not a rigid body, so that the fluid can act accordingly. So create FSI wheels. What have I done here? Oh, okay. So here, if I have a get mesh function in the tire, that means the deformable tire is the logic I use. You can do something cleaner, but it's just something to make it work. And if the tire is deformable, to my terrain, I add an FEA mesh, which is the tire's mesh. If it's rigid, it's the rigid body and the geometry associated with the rigid body. Great. So I just switched this. I commented the rigid tire JSON file out and I uncommented this, and hopefully it should be enough to run the sim with deformable tires. Yes. So this is expected. It's going to be really slow because the FEA, the 4 tire simulation is like, I would say, an RTF of about 600 to 1000. So it's completely dominated by that. But now you can simulate this vehicle with deformable tires instead of rigid tires on this time. Yeah, I'm not going to run it because it'll take a lot of time, but you can run it yourself. Okay, so that is how you change from like a rigid tire to a deformable tire, and that concludes all the show and tell that I had. So now is the time to ask any code related or any other general questions that you might have. Yes. Yes. Let me find that for you. So in many of the demos, you will see this variable called snapshots, which does exactly that. Great. It's not in this demo, so I'm just going to search it in all my demo files. I'm trying to find like a CRM terrain specific. Yeah, so there's one for the earlier demo that we saw. Okay, so this is the API. This is just setting the file name, and you say write image to file with the visualizer. Yeah, so I think we also have a CH wheels vehicle visual system. So I think you just use that visualizer to call write image to file. Let's see if we can do it. I wonder if I have snapshots. So this is Viz. Sure. Going back to rigid terrain. Hmm. So I didn't write it. So I'm thinking why. Oh yeah. Uh, yeah. So that's the API to write a file. Yep. Any other? Okay, great. So you get back, I think. I don't know when this was scheduled to finish, but I think I'm done. Thank you all for patiently listening to me, and it was great. It was great presenting this work. It was very fun. Thank you so much.